Hello, everyone. Thank you for tuning into our recording for this week's meeting. We have a statistics workshop for you guys today using JMP, so we hope you guys are excited for that. So here is our schedule for the last 2 weeks for what we have planned. Today we are recording this workshop and it should be going out Friday. And next week we have a Tableau workshop, which should be just scheduled normally like any other workshop. I think this week was just an exception because we were running a bit late with our logistics and stuff. And then week 9, we think we're going to have a joint meeting with Cal Poly Data Science, but if that doesn't work out, then we will have a Python workshop for you guys. So here is the Defining Her Future conference information. It'll be on March 5th, 2021 from 9:30 a.m. to 3 p.m. You can scan the QR code in the bottom right corner to get more details on that. And this is a great opportunity to connect with aspiring leaders and business professionals from companies such as EY, Adobe, Twitter, LinkedIn, and you could also win some amazing giveaways that are going to be held during that conference. And any Cal Poly student from any major is welcome here. And it is a free conference that we feel would be a great opportunity for all of you.
All right, so the internship of the week that we're highlighting is the Amazon Business Operations Analyst internship. So this internship will be taking place over the summer in Virginia or Washington, D.C., and they're looking for someone that's a third or fourth year. So what you'll be doing is developing metrics and reports to manage sales pipelines, build revenue, and quota attainment. And they're looking for someone with experience in Power BI, Tableau, and SQL. So if this sounds interesting to you, definitely check it out. If you haven't already, be sure to follow us on Instagram. And if you want to contact us, our email is cpquack@gmail.com. And this is the QR code to join the mailing list if you're not on it already. And if you haven't, please join our Slack channel. Then you can get weekly updates about the meetings and get information about internships and much, much more. And it's a much more direct way to communicate with us.
The link will be in the description for the YouTube video.
And we have a suggestion box. If you scan the QR code and just let us know your suggestions. We're always trying to improve Quack, so we'd love to hear any of your feedback.
Cool. So today's workshop is going to be a JMP workshop. I'm sure you guys have used it in either your Stat 251 or 252 class. If not, don't worry. It's a pretty shallow learning curve. So we'll jump right into it right now. We'll be going over transformations using simple linear regression and interpreting the values that you get from the regression output. Okay. So the link to access the software through Cal Poly's virtual software computer lab will be in the description of the video. You can click on that and you should end up over here. And then from here, you click on computational. And what it essentially will take you to is a bunch of applications. And then you just click on Jump Pro 15 there. And it should take you to this screen right here. So after you've reached here, it might take a minute or two to load. After you get here, you go to click on File at the top left, and then you click on Open. And then with this virtual computer lab, it comes already preloaded with some good data sets. So this is the default directory. And if you scroll down a bit, you can see all these data sets, which are already integrated into JMP. We will be using this CARS 1993 data set. So once you find that, click on it and then click open. And then it should pop up like this with a bunch of these cells and columns and rows, just like they do have in Excel. So this is your main view right here. After any regression output that you close out of, you should be redirected back here. And yeah, these are different variables that we have up here. So before you do any regression, you kind of want to know what your objective is. So I guess taking a step back, what simple linear or what linear regression is is essentially creating a model using the least squares of the residuals and the predictor model to create a model that is accurate, that is the most accurate given the data that you have. So this is also called ordinary least squares regression, or OLS regression, which you may have seen in some of your stats classes. But it is the main focus point of what you can do with the jump. So like I said, you need a question or some sort of objective before you go into any regression. So for us, we will be asking the question, does the max horsepower affect the mid-range price of a car? And with your question, you also need a hypothesis. So for us, we would assume yes, because typically those cars that are more technologically advanced are faster and therefore more expensive. So what this means is that we are looking for a positive linear relationship between those two variables. So going back to our jump program here, what we want to do is you want to click Analyze on the top bar and then click Fit Model. And it should pop up this window right here. So what we are going to do is, so because we want to predict the price, we'll be dragging mid-range price to our y variable right here. So our mid-range price is going to be our dependent variable, which is going to be dependent on the maximum horsepower of that car. So we're going to drag max horsepower to the big square or big box that's right here, which is essentially where you put all your x variables. And then under emphasis here, we want to switch that to minimal report so we don't get any windows or statistics that we won't need for this sort of problem. And then our personality is going to be standard least squares, or the ordinary least squares regression that I mentioned before. So once you have that all set up, you click run. And you can see, just by looking at it, as soon as it comes out of the output, you can see that there is a positive linear relationship between the two. So we do see that we do have something here and that our hypothesis isn't completely incorrect. So before we look at any of these other numbers here, there are 4 assumptions that we need to go through before we can actually start to get into the numbers and analyze what all this means. And those 4 assumptions are the line assumptions, which stands for linearity, independence, normality, and equal error variance. So with linearity, we can see that it is relatively linear. There's no parabolic shape going this way or parabolic shape going this way. So we can assume that it is linear, but one other way you can check that is you can click on this red hotspot in the top left and then go to row diagnostics, and then click plot residual by predicted. And you can see that there's about an equal amount of points above and below that line. And what this line essentially is the residuals for the residuals between the predicted value and the actual value. So we can see that there's no apparent linear or apparent curve shape or nonlinear shape. So we can assume that linearity is satisfied. And then with independence, we can assume that it is independent because it is not time series data. And typically time series data is the one where you do have to check for independence since, the longer time goes on. It could be the response variable could be dependent on that. So we can assume that it is independent. So next we want to check normality. So for this, we go back to this red hotspot at the top left. We click row diagnostics, and then we want to plot residual by normal quantiles. And then once we click that, another output should pop up on the same window. And we can see that these points are relatively within these two curved bounds right here. But if there were any points that were further out and not within these bounds, either over here or over here, then normality would not be satisfied. So we could assume by just a small margin that the normality assumption is satisfied here. And then next we want to check equal error variance. So to do that, we have to reference back to our residual by predicted plot that's up here. And what we are looking for is any fanning shape in the residual by predicted plot. So what that means is that, the further the mid-range price, the predicted mid-range price goes in either right or left, the more variance there is between the residuals, the plotted residuals. So we can see that there's indeed a fanning shape, which is fanning right, which means, as you can see, that the points are becoming more spread out as the predicted mid-range price gets higher. So what that essentially does is that invalidates our model, and we can't use it to come up with any prediction expressions or interpret any of these correlation numbers. So in order to fix this, we can transform our y variable, because one rule of statistics is that if equal error variance is not satisfied, you typically transform your y variable in either in two directions. So if you could either increase the exponent or decrease the exponent. But luckily, JMP has something that can determine what that best exponent is to transform the y variable. So to do that, you click on this red hotspot again, and then under factor profiling, you click Box-Cox Y transformation, and it'll pop up this output right here. And then we can see that the best transformation to do, so this is the exponent that you should be raising the y variable to. And for this regression, or for this model, it would be negative 0.133. So to create a new linear regression with that transformed y variable, we can go click on this hotspot for Box-Cox transformations, and then click refit with transform. And it'll already input the one that this output suggested. We click OK. And we can see that by just looking at the residual by predicted plot, there's no more fanning. And there is no apparent curve shape, which means the rest of our assumptions are correct as well. And then just looking at the normal quantile plot, we can see that it actually does get better. So now all 4 of our line assumptions are valid, and now we can go ahead and interpret some of the statistics in our output.
All right, so one thing that you may want to check after you've transformed your data is how well your model fits your data. And one thing we can do to check that is check the R-square. So to find the R-square in JMP, we check under summary of fit, and there's a value that says R-square, which is 0.678829. So essentially what R-squared is, it's the percent of variance in the y variable that can be explained by the x variable. So if we want to interpret it in terms of in context of the problem of the data, we can say that 67.9% of the variance in the mid-range price can be explained by the maximum horsepower of the vehicle. So R-squared can have like a highest value of 1 and a lowest value of 0. So the higher it is, the better the model fits the data. So one other thing that we can look at are the actual parameters, and we can try and interpret them. So you can scroll down a bit. So to find the parameters, we go to parameter estimates. So the one thing we can look at is the intercept, which is the predicted mid-range price when horsepower is 0, and that is 43.03. And in the context of this problem, it doesn't really make sense because you can't have a car with a horsepower of 0. So we can just kind of like ignore it for this in this case. And one other thing you may want to check is how much the data varies from the predicted values. And we can check that by looking at the root mean square error. And that's also under the summary of fit, and that's 4.523. So that means that the typical deviation of the actual mid-range price will vary from the predicted mid-range price by $4,523.
Yeah, and then when we look at our coefficient for our x variable, we can see that it is 0.1248. But because we have transformed the y variable, it can't be a direct interpretation saying that, one horsepower increase results in a $124 and 88 cent increase in the mid-range price for the car. But the way you interpret that is essentially just saying down here that a 1 horsepower increase reflects an increase in the mean estimate of the median or the mid-range price to the negative 0.133 by 0.125 or $125 about. And then we can put that all into the prediction expression, which can be shown down here. And yeah, that is your simple linear regression equation.